Hello, welcome to Chapter 2, 8.1. And I'm talking kind of softly because it's weird. The power went out. And so I was like, all right, I got battery power on my tablet. I can still make a video, but I can hear everybody outside and I can hear my family downstairs. And it's kind of weird. Anyway, so I didn't have internet access to put a picture of a teacher. So there's your teacher right there. You think of that person while we're going over this. And this video is about accuracy and precision, leading into something called significant digits. And it really talks about lab work and lab methodology. So I'm going to start with a definition of accuracy and precision and then proceed from there. All right. Accuracy versus precision. Now, those definitions, the correctness of a measurement. It's really hard when you do lab work to know if you're accurate, because in order to know that you're accurate, you also have to know the correct answer. And sometimes you'll know the correct answer. And the type of lab work we do, we're just verifying things. But in pure research, you don't know what the correct value is. So it's when you look at accuracy, accuracy comes from correct methodology, which means that you have to do your research correctly. So, one of the ways to be accurate is to make sure that you have good hand technique when you're using the equipment, that the equipment is calibrated correctly, and that you do many, many, many trials of an experiment and then take the average of those trials to be accurate. Now, precision is about being able to reproduce your results. And you were probably taught in middle school that precision meant the number of decimal places. Well, you can be imprecise, or precise rather, with other means. It's a matter of how many of the numbers in your measurement can you reproduce. The more numbers you can reproduce, the more precise your measurement is. So a lot of times when they're teaching this, and it's an okay analogy, but I don't like it because it's what they call a flawed analogy. And I'll tell you why in a moment. When they talk about accuracy, they tend to talk about, and I think your book uses this as an example. What if we had an archer and an archer was shooting arrows at a target? All right, so we got our target, and there's our bullseye and our target. And it says, well, if the archer, let's go ahead and do this. Copy, paste, we'll put another target here, and then copy, we're going to paste the second one. All right, so I got 3 targets I can deal with here. Let's grab these targets and move them down so I can show you all 3 things. I'm going to show you accurate, and precise without being accurate. So in the archery example, they say, okay, we're going to shoot some arrows at a target, and if you hit the target in the bullseye, then you are considered accurate. And if you hit the target of the bullseye over and over again, like 3 different times here, then this is considered accurate and precise. And then in the last target, if you hit near the same spot with your 3 arrows, you are precise because you're reproducing your result, but not accurate. All right, here's why I don't like this analogy. Because the thing with archery is you can practice archery and you can become more accurate as you get better. But this also implies that if you practice archery, you can improve your precision. And you can. If you're an archer, even if you're missing the bullseye, you can aim the arrow and hit a different area over and over and over again. But the thing with precision in the lab is, yes, accuracy, you can practice your technique and that will help you become more accurate. But you can practice your technique 1,000 times and it's not going to make you any more precise. Accuracy is controlled by the experimenter. He has the correct methods. She has the correct hand skills. He or she has a machine or a piece of equipment that is calibrated correctly, designed to work correctly. However, the precision is based upon the instrument itself. Some measuring instruments are more precise than others, and you can do nothing about that other than change out the equipment. So let's say I have a graduated cylinder that's precise to plus or minus zero point 0.1 milliliters. The only way to get more precise would be to get a different graduated cylinder that's precise to 0.0001 milliliters. So it's the equipment that determines the precision, not the person doing the experiment. The person doing the experiment controls the accuracy, but the equipment controls the precision. All right, so we're going to get into, what we can do about all that and how we deal with it in calculations. But first, a little bit of background information. There are two types of labs. One is the quantitative type, where you're making numerical measurements for your data. So your data is based upon numbers. Where qualitative labs, your data is based upon values that are not measured. Okay, and what drives me nuts is when kids say, "Well, quantitative you can see, qualitative you can't." And or qualitative you can see, quantitative you can't. That's not true. You use your eyes to measure materials, whether you're doing it quantitative or qualitative. You're going to use your eyes. You have to be able to see the instrument. Here's a better example of what quantitative is versus qualitative. Let's say we're dealing with green. Well, I can say grass green is a piece of data. I'm describing the solution, and I record in my lab book that the solution is grass green. Maybe it's transparent, that sort of thing. There are other descriptors I can give to it, but I'm going to call it grass green. Now, if I take that grass green solution and put it in a spectrophotometer, I can measure the wavelength of the light that it absorbs or reflects, and maybe that wavelength comes out to be something like 540 nanometers. Well, 540 nanometers is the quantitative description of green, where the descriptor grass for grass green would be the qualitative version. Now, both type of lab work is equally important. Sometimes, in order to understand something, we just have to know it's present. We don't have to know how much of it is present. And then that would be qualitative analysis. But sometimes we do have to know the percent composition. We have to know exactly what the mass is, what the volume is, etc. And that would be quantitative analysis. And I try to do a lot of both types when I teach lab. Another definition. In the lab, we might say, let's take up a powder like sodium chloride, and let's find the mass of it. Or other times I'll say, hey, let's take sodium chloride and let's weigh out 2 grams of it. It's a misnomer. I really shouldn't do that. I use mass and weight interchangeably as terms, and I'll explain why in just a second. But they want you to be clear that there is a difference between mass and weight. Mass is the amount of material, and weight is that material as it's influenced by gravity. But do understand that your balances that you use in the lab, they are calibrated to adjust for the gravitational pull of the Earth. So we don't measure mass in chemistry by newtons the way you might in physics. Instead, what we're going to do is we'll just measure it in grams. And the reason for that is that we don't intend to do any lab experiments on, let's say, which planet? I'm not going to say Uranus because then people get upset. I'll say Jupiter. We're not going to do any experiments on Jupiter because we're not going to Jupiter. That would be silly. We're going to do all of our experiments on Earth, so we don't need to recalibrate our machine to adjust for the gravitational pull of Jupiter. So I'm going to use the term mass and weight interchangeably, but there is a difference. Mass stays constant regardless of where you are in the universe. Your weight, however, changes based upon gravitational pull of the largest object next to you. When you are taking measurements in a lab, the format is whatever you write down, that is the last digit, the digit furthest to the right of the decimal, or the digit in the ones column if you have no decimal. Whatever is the digit furthest to the right, that is called the estimated digit. What we're telling people is that the precision of the instrument ran out in that column. And I'm going to show you a couple of examples what I mean by taking a look at volume measurements and taking a look at measurements using a ruler. But no matter what you write down in your lab data, that last digit is estimated. We are guessing at the digit, and I'll show you why. All right. Suppose we had these two different containers. One is a beaker, and there are markings on the beaker for every 100 milliliter. And the second one is a graduated cylinder where there's markings on it for every 1 whole milliliter. Which one's more precise? Well, we know because of the markings in our sophistication that the one that's marked for every 1 milliliter is going to be more precise than those that only have measurements for markings for every 100 milliliters. The markings, by the way, are called graduates. So let's say we have to make that measurement. Okay. First of all, when you're making a measurement, you have to be eye level with the graduates. If you are above the graduates or below the graduates, it introduces something called parallax, which means that your eye is not going to read correctly what the markings are. It's a visual distortion created by binary vision, and we have binary vision. We have two eyes. So there's a lot of great things about binary vision. Parallax is not one of them. So to avoid parallax, we go to eye level. Next, whenever you have a fluid, it's going to have a meniscus curve. Now, these bend downward. Some of them curve upward. But wherever you go, you take the lowest part of the meniscus curve, and that's going to be your measurement. So we would make our measurement here. Well, what do we know about this? We know the answer is somewhere between 300 and 400 milliliters. Now, we could make an estimate in the tens column of what the value is, and we should, because we know it's greater than 300, we know it's less than 400. And no matter who looks at this beaker, they're all going to put the first number down as 3, somewhere between 300 and 400. Now that second number, some of you might be saying it's about halfway, 50, maybe a little less, 40, or maybe a little bit more, 60. I'm going to write that it's 340. And then that's going to be my recorded value. So what does that mean? That means we're telling people that this tens column, pardon me, our tens column was our estimate. What do we mean by estimate? We mean that there were no markings there to guide us. There were markings here in the 100s column. Every 100 we had a marking, but we had no markings here in the tens column. And the rule is the last digit tells you where the estimate was. So any digit after that would be zeros. Because if we're not sure about the 4, because there's no markings for it, then we certainly don't know the digit in the ones column either. So you estimate one column, and this would be the tens column. So if you wrote 350 milliliters for this, I would have given you full credit for it. If you wrote 360 milliliters, I would have given you full credit for it. Or if you wrote 340, I would have given you full credit. But if you wrote 352, I would have marked it wrong, because there's no way you can estimate the ones column using this device. Okay, this device, however. All right, so we go eye level, and we're going to focus right here where they're looking, and their meniscus curve, they're saying, falls right on the line. Okay, so we know the answer then is going to be between 60 and 70. So we could put a 6 there. And if we count the places, this is going to be, looks like right on the 7. So we would say that this is 67. Now we know it's that number. We know the ones column because there is a graduate for every 1 milliliter. However, there's none for the tenths. So we're going to estimate the tenths column. If it falls right on the line, then our estimate is 0. So we would say that this is 67.0 and that this last digit is an estimate. What does it mean? It means that there was no marking for the tenths column. So 67.0 milliliters would be appropriate. And if we want to say how much error there is, we could say that it's plus or minus 0.1 milliliters. I don't like students to do this at this level, though, because there is a calculation using probability and statistics that you should do in order to make those sort of assessments. Okay. What if we had something like this? I'm going to draw my little grad cylinder here, and I'm only going to draw part of it. Let's say we have 1 milliliter here, and then 1, 2, 3, 4, 5 tenths, 6, 7, 8, 9, 2 milliliters. And let's say our fluid has a meniscus curve that curves downward, and we're going to stretch this a little bit. And let's say our meniscus curve looks like this. Here's our fluid, right? And then here would be the top of the fluid. You know what? I'm not going to draw it that way because I think that's going to be confusing. Let's get rid of it. Let's just draw the meniscus line. My three-dimensional drawing isn't particularly good. All right, so you're going to pause the video, record what you think. Again, the units are milliliters. Record what you think that this volume should be. I'll wait for you. Hey, you're back. Okay, I know the answer is greater than 1, less than 2. So the digit I'm going to write is 1. I also know that if this is 0.5 and this is 0.6, that the answer is somewhere between 0.6 and 0.7. So my second number is going to be 0.6. Now, everybody who reads this, who knows how to read a grad cylinder, should repeat the 1 and the 6. That's our precision. That's our repetition. Everybody will say 1.6, but what will be different is when people make an estimate of what the next digit is, it may be a little different from person to person. I'm going to say that the next digit is 1.63 milliliters. You might have said 1.64. We might zoom in and see that it's 1.62. It doesn't matter. The last digit is our estimate anyway. So in terms of precision, if I had 3 different people look at this, person number 1 might say 1.64 milliliters. Person number 2 might say 1.65 milliliters. Person number 3 might say 1.62 milliliters. What's the correct value? We don't know. Because you can always add one more marking to your instrument. These decimal places could go on to infinity if we had the equipment for it. So what you do to get an accurate reading, we talked about precision. Again, the precision here is that everybody is repeating the 1.6 part, even though they're not repeating the last number. The accuracy would be to take an average of a large amount of samples. Okay, why? Well, the analogy is like flipping coins. If you flip 10 coins, you should get 5 heads, 5 tails on average, right? But if you flip the coins, is it possible for you to get 6 heads and 4 tails? Absolutely, right? But did you do anything wrong? No. It just so happened randomly. It was out of your control. 6 heads and 4 tails came up. Now, you may flip them again and get 4 heads and 6 tails to balance that out. But is it possible to flip the coins 3 times in a row and get 1 heads out of 10 the first, 3 heads out of 10 the second, 4 heads out of 10 the third? Well, of course it is. But if you add them up, then your average is only 2.67 heads out of 10, when we know on average we should get 5 heads and 5 tails. You got to keep flipping the coins. And that's what lab is about. We got to keep repeating. Remember scientific notation? I said repeat, repeat. Good methodology is that we are going to repeat and then take an average. You should do a minimum. Statistically, statistically you can get away with a minimum of 3, but you should, for good methodology, let your minimum be 19. Repeat the experiment 19 times. So how do we do that in the lab? Well, in high school, we work as a group, and then I'll put a group of 5 or 6 people together, and they'll do the lab 3 or 4 times each. And then we bring the data together, and then they're impressed at how close to the real answer we can actually get. All right, so let's go back and take a reading. Again, let's zoom in here. This is in milliliters. I'll write that down. Please determine the volume using this grad cylinder to the correct number of significant digits, which means the correct precision. Go ahead, I'll pause. I'm back. We know the answer is between 20 and 30. We know the answer is between 25 and 26. And we know the answer is just below the 26 mark for the bottom of the the meniscus curve. So we're going to make this, I don't know, 25.8 milliliters. Where's my estimated digit? It's in the tenths column, which means that this is going to be precise, plus or minus 0.1 milliliters. This right here, this plus or minus 0.1, this is called indeterminate error. Some people call it random error, which means that sometimes people guess too high on the last digit, sometimes people guess too low. Let's try one using a ruler. Here's my ruler, and look, the arrow is pointing right on the line. So if the arrow is pointing right on the line, what would this measurement be to the correct amount of precision? I'll pause and wait for you. Hey, I'm back. Okay, so we know the answer. Here's my 2 centimeters right here. Here's my 3 centimeters right here. And then this is broken up into 10 tenths. So we know the answer is going to be between 2 and 3. Sorry. Oh, I hate when that happens. Glitch. Here we go. We know the answer is going to be between 2 and 3. So the first digit we're going to write is 2. 2 point something. Can we go to the tenths column? Yes. There's markings for the tenths. So we're going to make this 2.6. And our estimation would be to the 100ths column. There is no marking for the 100ths column, but we still have to include an estimated digit. And since this arrow falls right on the mark, we're going to make that estimated digit 0. And then we put in our units. Our error would be plus or minus 0.01 centimeters. Now, those devices where you have to read the graduates are called analog devices. The ones that use the computer probes and processors are called digital devices. So if we're measuring the temperature using this first one, what would be the precision? Well, the way a digital device works is that whatever they list as the last digit, this is the estimate. This is where my error is. So if I was writing this with error, I would say, all right, this is 28 degrees C plus or minus 1 degree C. Right? We have error in the ones column. A digital device, the error is in the last digit. The digital device always estimates the error for you. So if we come down to this one, here's a different temperature probe. What is the precision of this device? Well, we would write 235.4, and the error is already estimated by the computer. So it's there in the tenths column. So we could say this is 235.4 plus or minus 0.1 degrees C. Let's go back to our little slideshow. All right, so we did that, we did that, we did that. Okay, there are 3 types of error that you have to deal with in your lab. The first one is called determinate error, systematic error. Some people call it human error. In other words, you messed up. Now, you messing up may not necessarily be your fault, but it's something that you can deal with and get rid of. In other words, what if you have a miscalibrated instrument? Well, then you take the instrument to a technical place and have it calibrated. Or you read the instructions and calibrate it yourself. It's like having an out-of-tune piano. You're going to have to get the piano tuned. It has to be in the correct calibration. If you have flawed techniques, in other words, you don't know how to read things properly, then you can practice that technique and improve that and get rid of the flaw and then get rid of that determinate error. Error in methodology means that the way you're approaching the lab is incorrect. You're not controlling the variables correctly, so something is interfering with your data. You have to find out what that is and get rid of it. Statistically, the way you can figure out is if your lab has been acted upon by determinate error is to take a look at this. Determinate error is always in the same direction, which means that if there's a mistake, it's always going to be too low compared to the correct value. If there's a mistake, it's always going to be too high compared to the correct value. But if you make a mistake and you have determinate error, you're never going to get a combination of, oh, sometimes it's too high, sometimes it's too low, and then hopefully it averages out. That's not going to happen. It's always going to be wrong in the same direction. That's what they mean determinate. You can determine the direction, and then that will tell you that you've made a systematic error. So in other words, I always tell students, look, determinate error in a lab, if we find there's determinate error, we're going to hunt it down, we're going to get rid of it, and then we're going to redo the lab. Now, second type of error is something called random error, or what's called indeterminate error. And the reason why they call it indeterminate error is you cannot predict in advance which direction the error is going to be in. Sometimes it's too high, sometimes it's too low. A good example of the indeterminate error was what I was showing you with the estimated digit on a device. Some people estimate too high for that last digit. Some people estimate too low. But if you do the lab enough times, you can get that error to cancel out. In other words, you're not in control of the error, but if you do the lab enough times, it will cancel out and go away. Now, how much error you get is based upon the instrument. Again, the only way to get a smaller estimated digit is to use a more precise piece of equipment with more markings on it. So in other words, you're not going to be able to control this error. It's going to be in there. Whether it's digital or analog, the only way to deal with it is to do the lab many, many times so that the error cancels out. Again, like flipping the coins. If we flip the coins enough times, we will get 50% heads, 50% tails. But if we only flip the coins once, it could be 8 heads and 2 tails. So you're not allowed to say, my findings say that flipping a coin, 80% of the time you get heads. That would be incorrect. And the third type of error is something called propagated error. And that occurs when you make a measurement and then substitute it into an equation. For instance, suppose we have density. And density is mass divided by volume. Well, whatever amount of error we have in our estimated digit in the mass, and whatever amount of error we have in our estimated digit in the Grad cylinder or picnometer, depending upon what we use for density, at the higher levels we use something called a picnometer, that is going to be propagated, which means it's going to go from your measurements into your density calculation. So your density calculation is going to have error in it as well because your mass and volume measurements have error. I want to talk real quick about something called Gaussian statistics. Getting rid of this error. All right, what do we mean by a Gaussian curve? A Gaussian curve is something they call, another name for something called a normal distribution curve. Let's say, for instance, we have the number of heads flipping coins. And out of 10 coins, so we could get 1 head, 2, 3, 4, 50-50, 6 heads, 4 tails, 7 heads, 8 heads, 9 heads, 10 heads. And then we go into the lab and we start flipping coins and we start recording the data. All right, let's say the first time we flip, we get 5 out of 5 heads, 5 tails. Next time, we get 2 heads, 8 tails. Next time, we get 3 heads, 7 tails. Next time, we get 8 heads, 2 tails. And then we get 5 and 5 again. And then 4 and 6, 6 and 4, 4 and 6, 7 and 3, 6 and 4, 4 and 6, 5 and 5, 5 and 5, 1 and 10, 9 and 1. And all of a sudden, our data starts to look like this, where we get a lot of times very close to 5 out of 10 being heads. If we were to graph this, the shape of our curve looks like that. That's called a normal distribution curve, where the height of the curve represents our average. Sometimes they call that average X bar. X bar means that you took a lot of data trials. If we're doing the lab right, our data should resemble a normal distribution curve. Sometimes our estimates are going to be too low, and sometimes our estimates are going to be too high, but most of the values are going to be close to the average. And when we take the average of all things, that's going to be our correct value. A Gaussian curve has something called a standard deviation. Now, there's an equation for figuring this out. But if they say that the data lies within plus or minus one standard deviation, that means that's the formula they use to determine where 68% of your data trials should fall. Now, there's also something called a second standard deviation. If we go to the second standard deviation, away from the average, more data falls into that curve. Here's how it breaks down. You can expect about 68% of your data trials to be within plus or minus of the average one standard deviation. You could expect another 27, so 95% of your data to fall within two standard deviations away from your average. All right, so what does that mean? Absolutely nothing at this point. What it means is that because of propagated and indeterminate error, we don't always get the same result every time we run a lab. What we do is we record the results, we keep a statistical finding of them. If we do the lab long enough, we can see that we're getting a correct average. If we get this normal curve, we're getting a correct average. Now, what happens if we run a lab, let's say, and we start getting data points all down here, all of them way too low compared to the average, or the known accepted average? That means we have determinate error, because we can determine that every single trial is going to be less than the average. That means there's something wrong. All right. If we're taking a look at individual data trials, what can we say statistically about something that falls within plus or minus one standard deviation? And the answer is nothing. Once you get this standard deviation, there are other statistical analysis that you can do, and I recommend that you take a prob in stats. You take AP prob in stats sometime before you graduate high school if you plan on doing research, or at the very least make sure you take it your freshman year in college, because probability and statistics is very closely linked to research analysis. So if you get a data point within one standard deviation, here's what it means. It means, well, most likely there's nothing wrong with your data. If it's within two standard deviations, all it says is, look, it's probably okay. There might be a problem, but we're not sure. And if it's outside of two standard deviations, really low or really high on this curve, then it says, look, there's probably an error here that you could have controlled, but we're still not sure. So if you have data that falls within one standard deviation of the average, that's very normal. Within two standard deviations, that's probably okay. Outside of two standard deviations, you might want to consider redoing that data trial because there might be something wrong with it. Of these three normal distribution curves, which one represents the best precision? Okay, the one with the best precision has the lowest range of values. That means that your data is tighter and closer to the average per trial. So this one with the high, very large maxima and a very small range would represent the most precise of those data sets. And that's all I got for you. Next time I'm going to talk about how to apply significant digits in the error and how to deal with scientific notation. Thank you very much.